My name is Radu, and this session is about indexing and searching logs with Solr and a few things that should help make it faster. So to give you a bit more context about me, I do search consulting at Sematext. I also work with logging tools such as our syslog, logstash, Apache Flume as part of our logging solution, which is called Logzine. And I also combine a bit of both when I work with clients that want to develop their own logging solutions. So for this session, I prepared a bunch of benchmarks that I ran on EC2. And the big question that I wanted to answer was whether it's worth fiddling with settings and doing your own performance testing in order to optimize. And to me, at least, the answer was yes, because I could get 30 times more logs stored with 30% less cost between the first run and the last run. So before I share the results, I wanted to define a few things, like what I was tuning for. And I think most use cases are about tuning for capacity. So you're probably not interested in the ultimate search performance that you might not need, or ultimate indexing throughput when you're not producing that many logs. You're probably interested in storing as many logs as possible onto as little hardware as possible, while still having decent performance, still getting the solution usable. And that obviously is kind of a fuzzy concept. So I tried to organize it a bit. And on the indexing side, I think the challenge is to be able to index as many logs as they are produced. So as long as there's enough indexing performance for what you produce, I think that tuning further doesn't really help, especially if you sacrifice search performance for that. And I will talk a bit later about how can you determine whether indexing performance is enough. On the search side, I don't think many of us worry about search concurrency because logs are not searched that often. So that you have many parallel searches, but individual searches have to return in a decent amount of time. And that obviously depends on your queries and also on your patience. So I had to come up with some assumptions, and I think there are two big kinds of queries that are used for logs. One is for use cases where you need to do like some sort of a grep, when you aggregate logs from multiple servers, multiple applications, and you want to debug them in a centralized way. And I guess when you're debugging, ideally, it should be pretty snappy. One general purpose instance for running Solr, and one compute-intensive instance for feeding the logs to Solr. And to do that, I had a bunch of Apache logs in a file, and I would use a Python script to read the file, parse each bit of the log in its own field, and then index those logs to Solr. I started Solr with 15 gigabytes of heap, which was half of the total amount of memory. I left the rest for OS caches. And my two queries that I was talking about, the debug query and the charts query, looked a bit like this. So the debug query was searching for a keyword in a specific field, in a specific time range, and sorting logs by timestamp. And the charts query was faceting on 3 different fields. 2 of them were string fields, the status, the reply and the IP field, and one was an analyzed field, the user agent, over which I wanted to build like a word cloud. So the first result looked a bit like this. The indexing performance was pretty constant at about 7,000 events per second. The debug query was pretty fast. It was under 200 milliseconds for the whole time. And but the facets were obviously much more expensive until they passed the 5-second mark that I've set. And when they did that, I had about 10 million logs stored in there. So my capacity was 10 million logs. And it was determined by the fact that facets were getting slow at that point. And they were super CPU intensive. I could see all the cores going to 100%. But on average, CPU wasn't really hammered by the indexing. And that is because the feeder instance was using up all the CPU in order to generate that 7,000 events per second. So that raised the question of whether that was enough. Was it that enough indexing throughput? And it obviously depends on the use case. But I think there are 2 major factors that when you know them, you can determine whether you have enough indexing throughput or not. One of them is how long do you intend to keep your logs? And because for the same capacity of, let's say, 10 million logs, if you're indexing 1 million per day, you need more indexing throughput than when you're indexing, and you keep them for 10 days. You need more indexing throughput than when you have 1/3 of a million per day and you keep them for 30 days. But if you still need to index 1 million logs per day and you decide to keep them for 30 days instead of 10 days, you'll still need the same total amount of indexing throughput, but it's not the same capacity. So for 30 million, you probably need 3 of those servers, and each of them would index 1/3 of a million logs per day. So it really is that for the same capacity and the same server, like you're doing a performance test, if you decide to keep logs for longer, you would need less throughput. In this case, my 10 million log capacity was filling up at 7,000 events per second in less than half an hour. So if the retention time was more than half an hour, then on average, the 7,000 events per second was enough. However, you also have spikes in generating logs, so you need to account for that. And what I've seen in our logzine is that some people have up to 10 times the average amount of logs can be a spike. So if you want to account for that, you need to divide or actually multiply the retention time with what can be your spike. So in this case, I thought that with this 10 times the spike assumption, if I would hold logs for more than 5 hours, that 7,000 events per second would have been enough. So to increase capacity, the first thing I did was to enable auto soft commits and to make hard commits rarer. And this helped. This helped increase the capacity with about 10%. Mainly because I wasn't doing a commit and then a search. I was searching directly, and that was a bit faster. Then I tried a bunch of things that didn't really help. One of them was to make commits even rarer. Another one was to omit norms, term frequencies, and positions because I don't really need relevancy. I will always sort by timestamp. That made the index a bit smaller and the indexing performance a bit better, but it was the same capacity. Then I tried to use caches more, and the first step was to make caches larger. This didn't help because I didn't have enough cache hits. So then I thought, okay, let's warm the caches up. Auto-warming didn't really help because it couldn't keep up with indexing because it's running only on one thread. So I ran my own queries from a script, and I tried various intervals, and it didn't really increase the capacity at all. Then I tried to disable transparent huge pages, which is a kernel memory setting that many database vendors said that if you disable that, you'll get better performance. It wasn't the case for Solr, at least not in this particular use case. And then I tried to tune the merge policy, but that didn't help either. I think that this is because if you merge more and you have less segments and searches are cheaper, you're also invalidating caches more. So it's kind of apparently evened out, at least in this case. What did help was to use doc values. So the two of the string fields I had, I set it to doc values because you cannot use doc values on analyzed fields. And I got another 10% improvement in capacity. But I couldn't help thinking what would happen if I would make the user agent field, which is a text field, if I can make it doc values. But it wouldn't have been a fair comparison to make a string and use doc values. So I first made it a string and ran a test like that. And I had a pretty big improvement in capacity. So that goes to show that if you have cheaper facets, you can have a whole lot more capacity. And then on top of that, I made it doc values, and I have another 100% almost capacity improvement. And in case you were wondering what happens if you lower the index, if you have a lower indexing throughput, well, how that influences capacity, in pretty much all the tests I've done here, you would get a capacity improvement of about 5 to 10% between a really high indexing throughput and a really low indexing throughput. The next thing I tried was to use time-based collections. So in this case, I was filling up the index in about half an hour. So I said, okay, let's make one collection for 1 minute, which is kind of the equivalent of holding data for 30 days and having one collection per day. And that worked really well in terms of search latency, and I had quite a big capacity improvement. But I got a lot of collections there, and finally I ran out of memory. So then I changed, and I made one collection every 10 minutes. I couldn't use like 1 hour, for instance, because within the first hour it would fill up and stop. So with every 10 minutes, I had slightly slower queries, and things were also sort of spikier. But I did get a whole lot more capacity. Still, it was running out of memory. There were lots of collections. So I increased the heap size to 20 gigabytes from the 15 before. And I also tried to make completed collections more compact by optimizing them. And at this run, things were pretty even in the sense that CPU, memory, and disk were all sort of used to their capacity. And I was getting over 300 million logs as the capacity. So these are pretty much all the software optimizations that I did. Time-based collections, doc values, and auto soft commits were the things that increased the capacity. I would still use a bunch of other things. For example, the changes that will make the collections a bit smaller. And one thing that I didn't get to try was to change the I/O scheduler, because the default I/O scheduler for Linux is optimized for magnetic disks. And for SSDs, the no-op I/O scheduler works better. But I didn't get to try that because in this particular AMI that I used, it was already, the scheduler was already no-op. What I did try was to use other instance types. I took the memory optimized instance, which has double the amount of memory, so I could afford a 30 gigabyte heap. It's also a bit more expensive, and it has one bigger SSD instead of two smaller ones that I could use in RAID 0 before. So I guess the SSD is the reason why I had a bit less indexing throughput, but the capacity was a bit higher at 370 million logs. If you can afford the 9 days, if you hold your logs for 9 days or longer. Then I also tried with the compute-intensive instance, which has a tad more CPU, but it has half the memory and is also a bit cheaper. But the memory was actually a problem because I had lots of garbage collection, and yeah, the capacity was about 170 million logs. So the general purpose instance was actually best for this particular use case, but I think the hardware issue is a bit more complicated than that because it depends a lot on the exact use case that you have. So for example, if you have more expensive charts, then you need more CPU, so probably the compute-intensive instance would have looked better. On the other hand, if you have less expensive facets or you don't use facets at all, you would have a lot more capacity, in which case the instance storage wouldn't have been enough. So that opens another can of worms, like which EBS to use and what other instances would be better. And another thing that might be worth trying is to use different instance types for the hot collections, the ones that are actively being changed, and the cold collections that are already done and optimized. Because it's a slightly different kind of workload, so different instance types might help here. Then I turned to the fact that it was super inefficient to have pretty much the same kind of instance to feed the logs as the instance to index and store the logs. And that was due to my very inefficient scripts. So I turned to one specialized tool for processing and log data, which is Apache Flume. For those of you who are not familiar with it, it's a modular tool. You basically have sources, which can take logs from files, from the network, stuff like that. You have channels, which can buffer data, and then you have sinks, which send the data forward to the next hop. In this case, I was using the Morphline Solr sync, which can not only send the logs to Solr, but it can also process them on the way. You can think of Morphline as you define, in the Morphline configuration, you define a bunch of commands, and you can think of it as the logs going through Unix pipes. So in this case, I was reading one line of logs. I was processing it with Gheorghe, which is a wrapper over regular expressions that can parse each bit of the log to its own field. Then I was generating unique IDs for Solr. You can do that in Solr too, but my Python script was generating IDs, so I thought I should compare apples to apples. And then finally, I was loading the data to Solr. And with this basic configuration, I got 2,400 events per second, but it was using only 3% of the CPU. And this sort of low overhead setup, I think, is very appropriate when you can install Apache Flume on all the application servers that you have. In which case, you can, as you add more servers, you also add your indexing. You expand your indexing throughput. So you only, in such a design, you really only care about scaling Solr and making sure it works well. But if that's not possible or not desirable, you can always have like centralized processing, and you can also have like multiple layers. And in this case, you're more likely to want to have more throughput from Flume. And the first thing to look at is batch sizes, because Flume processes stuff in batches. Like the source takes a batch of logs and puts it to the channel. The sink takes a batch of logs from the channel. And in this case, the Morphline Solr sync would send logs to Solr in batches. So I increased the batch sizes across the board. I also increased them too much, which got me worse performance, but in this case, that was pretty good, a pretty good value to use 5,000. And I also changed from the file memory channel, which is kind of the safe, slow way, to a memory channel, which is faster, but if Flume gets killed, you would lose the data that's in the channel. And you also have to make sure that you have enough heap to buffer all that data. And in this context, I got 10,000 events per second, so it's already a whole lot more than I got before with only 6% CPU usage. If you want even more throughput, you can paralyze, and this depends on where your bottleneck is. Most often, the bottleneck is the sync, because that has to do all the parsing work. It has to wait for Solr to reply and stuff like that. So you can use the load balancing sync processor to define more offline syncs, and then this load balancing sync processor would use all of them to send data to Solr. And with parallelizing, I got 24,000 events per second with only 10% CPU usage. And this was limited really by Solr, it was admittedly a default install of Solr. I could have tuned it for more indexing throughput, but it could have done even more. One last thing that I didn't get to try was what happens if you log directly in JSON. Because then you wouldn't need to use expensive regular expressions to parse the data. You could just read the JSON instead of grokking the logs. Then this also helps, for example, if the log format changes, then you don't have to adjust your parsing because it's still JSON, it still only has to read JSON. In the case of Apache, you can configure the log format to send out JSON logs, so that should help. Coming back to where I started, I said I could get 30 times more data with 30% less cost, and this wasn't due to hardware changes because, incidentally, for this particular use case, the general purpose instance was good, but it was because of time-based collections, doc values, and auto-soft commits. The 30% less cost came from the fact that you could use a much smaller instance for feeding the logs if you're using a specialized tool like Apache Flume. And if you want to tune it for more throughput, you can look at changing the batch sizes, using the memory channel, and parallelizing. So that's about it. I think we have a bit more time for questions. Can you wait for the microphone? Hi.
What was the cardinality of your faculty?
Sorry?
What was the cardinality of your faculty?
Well, I had 3 fields. So it was the status. The status field had very low cardinality because you only have a handful of statuses. The IP wasn't that big. I don't know, probably a few thousand, I guess. But the user agent string was kind of messy, especially since it was analyzed. I cannot say a number, but yeah. Can you get the microphone? Thanks.
What did you think about using Nginx over Apache and Kafka over Flume?
I don't know. I guess they're kind of equivalent. I wouldn't recommend one over another. It's just a matter of preference, I guess. Any more questions? Oh, okay. Can you?
Hi. You
Hi.
mentioned something about Solr collections based on like days or dates or whatever.
Exactly.
Can you go a little bit more details on that? Like, if you were to store, let's say, logs for like 2 weeks, is there like a preferred approach? How you went
Well,
about
if
that?
I would store logs for 2 weeks, I would make 1 collection per day.
And if you wanted to make it like into a rolling log, would you use something like a date expired, or how do you go about something like that?
Oh yeah, that's something very nice about time-based collections, because you can just delete a collection instead of deleting logs within a collection, which triggers merging and is much more expensive. So you can just have like a cron script somewhere that would every day delete the collection that expired. You're welcome. Any more questions? We have time. It's not even the blue. Okay. Can you get back the microphone?
Thank you. It's faceting again. What about this segment-based faceting? Shouldn't it help with scaling here?
What do you mean segment-based faceting?
Facet method FCS, I think it is.
I didn't try it.
Okay.
Not sure what you're. Yeah. Okay. Can you get the microphone? Can you pass the microphone on? Thank you.
Yeah, in the beginning, you mentioned about 1 million logs per day, and you had some statistical information. What is the approximate size of the log file?
Oh, these were kind of standard Apache Access logs. They were about 240 bytes for each raw line of logs. So made JSON, it's a bit bigger, but Solr also compresses it. So in the end, it's also about the same, sort of 200, 300 bytes for each document.
Okay, so if I have syslogs,
Yeah.
how would that translate? Because the syslogs is growing constantly.
Yeah, well,
So
yes, but every line is still, I think, even a bit smaller than Apache logs.
So every line, so you're saying every line within syslog
Yes.
is considered as
A document.
Okay.
Yes.
That answers it. Thank you.
You're welcome. Any more questions? Okay. Not sure if you can throw it.
You said that the batch size can influence it. Can you elaborate a bit more on that?
Yes. So by default, the batch size is for sending events from the source to the channel, and then on again is about 100. It's about 100. It sends 100 events at once, and the morph line sends to Solr about 1,000 at once. So if you have more hardware, like I had here with 8 CPUs and stuff like that, that is too little. So it has to do too many sort of cycles. And increasing the batch size increased performance. But then if you increase the batch size too much, then it has to wait to process every batch. So it's kind of a sweet spot. Like in this case, 5,000 was pretty much the best I got. When I went to 10,000, I had like 30% slower throughput. More questions? Okay. If you have any more questions, you can probably catch me at our booth. So I'll be glad to talk to you. So thank you.